Ladies and gentlemen, welcome to the Achema Highlight Webcast. Once more, it's a pleasure to introduce you to some of the topics that shape and change the process industry. This is meant to shorten the time until Achema actually starts, which is tomorrow, only 1 month away. So on the 22nd of August, we will be on the Frankfurt Fairgrounds, and we are really looking forward to meeting all of you there. In the meantime, however, we want to give you some food for thought and the opportunity to enter into discussion with us. So during our webcast, make sure to go to Slido with the hashtag Achema Highlight, ask your questions, and I will pass them on to our expert today. So don't hesitate to join us here. Now, these days we're talking a lot about the defossilization of the industry, or even the decarbonization, which is a bit difficult for the chemical industry that relies on carbon for a lot of its products. However, currently we have two sectors that emit carbon dioxide. So one is the energy sector, and the other one are the products the chemical industry produces when they are, recycled or when they are burned, they emit CO2. So we really need to close those cycles because, as I said, we can't really live without the carbon in the chemical industry. And closing those cycles requires new technologies known by keywords such as power to X or CCU, carbon capture and usage. And these are one of the biggest research issues of our time, which is also indicated by the fact that in 2011, the Max-Planck-Institut of Chemical Energy Conversion was founded. So you can see the connection between chemistry and energy. And it's my pleasure today to talk to the founding father and director of this institute. He's also a director at the Fritz-Haber-Institut of the Max-Planck-Gesellschaft in Berlin and one of the internationally most distinguished experts on catalysis. Welcome, Professor Robert Schlögl.
Welcome. Thank you.
Professor Schlögl, it's a pleasure to have you with us here today and to discuss really one of the hottest topics I think we have in the industry. And in my introduction, I already mentioned we are talking about several sectors that have to deal with carbon emissions. We can generate energy without emitting carbon dioxide, but we need carbon for many products. So why don't we leave just the energy system aside, focus on the chemical side of things, and try to close those carbon cycles we have in the chemical industry?
First, I would say we cannot generate energy, we can only convert energy, and we can also not convert all forms of energy without producing CO2. Think about fuels, for example, and think about materials like cement, glass, lime. They also will always produce CO2. I mean, we have to see that we need in the energy system a fraction of processes and also materials that will always generate CO2. And as you said in your moderation, we need to close this cycle. The ballpark of energy that we convert at the moment from coal, gas and oil for electricity generation, that we can of course defossilize. That is not a problem. But there is about a stock of maybe 30% of processes that we cannot not get rid of the carbon.
Now, one of those processes is, for example, the exhaust from steel mills. You're targeting this with one of your projects. Can you introduce a little bit to the C2C project? What are you researching there?
Yes, of course. Within a carbon cycle, there we have, of course, an emission, so a source, and the source is never pure CO2. So when we have such an off gas, then this is a complex mixture. We have to isolate the CO2 and purify it. And just to give an introduction, the purity of the CO2 that we need for chemical processes is orders of magnitude purer than the CO2 that you have in your brewery when you want to tap your beer. So the CO2 for beer tapping would immediately destroy all catalysts that we use. So separating the CO2 and purifying it is one of the issues. The other issue is, of course, the fluctuating source, because normally you have a feedstock in chemical processes that is constant in flow and composition. In a steel mill, this is not the case. It fluctuates all the time. So all the downstream processes that we look have to be able to accommodate a fluctuating composition. We use at the moment methanol synthesis and ammonia synthesis as two of the processes, and we test the conditions under which we can guarantee that we have a lifelong operation of this catalyst similar to standard conditions, but with this strange feed that is variable in time, space, and composition. That is the part of this of carbon to chem. The other part of it, what do we do with the methanol or with the ammonia, is a second part of the project. And here we use fertilizer synthesis on one side and fuel synthesis on the other side, and use in particular methanol as a platform molecule also for other chemicals. So it's a rich project that has many facets.
Yes, it sounds like a whole plant in itself, next to the steel plant. It will be, yes. Currently, carbon capture and usage is mostly at the lab scale. I think there's some demo pilot scale things around. But what are the biggest hurdles for the scale up?
Essentially the ones that we also study in carbon to chem. So I would say there are CCU projects that are significantly larger than lab scale. Also, carbon to chem has left the lab scale. We are now tons per day is our production scale at the moment. This is not lab anymore. But the problems why this is so difficult is indeed lifetime of the whole system and the system integration. Because in a normal chemical plant, there are simply different conditions than if you use such off gases and water electrolysis as feed for the hydrogen. That's a problem. So dynamic operation is not so easy.
Mm. To our audience, if you have any questions to Professor Schlögl, join me here in asking. Just go on Slido with the hashtag Achema Highlight and ask your questions, and I will pass them on. Meanwhile, I'll take the chance to ask some more, because I'm quite fascinated by this interaction between the steel mill and the chemical process. You just mentioned that this is really one of the big challenges you're facing. Are you also adjusting the steel mill operations, or are you just adjusting the chemical side? Is it even possible to rearrange something in the steel mill?
In the longer term, I'm sure there will be a readjustment, because at the moment people are thinking of replacing coal by gas in order to generate iron from iron oxide. There's of course always the saying of direct reduction by hydrogen. I'm not absolutely convinced that this is possible, because when you look into the thermodynamic equilibrium situation, then we learn that pure hydrogen is not a very good reactant in order to make iron, but CO is a very good reactant. So that means, I guess, yes, the processes in the steel industry will change, but I'm sure that the new processes will be not completely CO2 free.
Now, you mentioned already that you're targeting methanol and ammonia as target molecules. You mentioned also the role of fuels. Why are you not focusing on, let's say, higher value chemicals or large volume chemicals such as polymers, but rather on methanol as a chemical battery?
Methanol is always the first molecule that you make from CO2, is the easiest reaction that you can do. Methanol is a platform molecule. You can use methanol itself as a fuel, but you can make anything that you mentioned, can you make out of methanol. So that means once you have green methanol, you have everything that you want in the chemical industry at your disposition. And as we have so many different demands for carbon, as you mentioned, it is maybe a good idea to start with a common platform molecule rather than trying to invent many different fundamental processes that all tap into the CO2 sources. So one conversion from CO2 into a useful chemical, and from then on use standard processes. That is our strategy.
Yeah, sounds very reasonable, I think. Go for the target with which you can do the most. I remember from past years that there has been a lot of discussion whether carbon capture and usage really can help to tackle climate change, because the volumes are not so large that we need for chemicals. From today's point of view, what share of CO2 emissions will we be able to neutralize by carbon capture and usage?
In a final situation, we will not take any CO2 away from it, because if it's a closed cycle, then of course there is nothing to be taken away. And I think it is a misconception to think that CCU is a contribution of saving CO2. That is never the intention. CCU is necessary in order to keep carbon in the loop. And as you mentioned, we cannot have energy systems that are free of carbon. So that means in the transitory period, we will of course take some of the residual CO2 away. But in a final situation, there is no fraction to be taken away, because it's a closed cycle. And the size of the cycle is significantly smaller than the energy system that we have today, maybe 20% or something like that. But you should also remember that Mother Nature does it exactly the same way. And the CO2 cycle of Mother Nature is about 60 times larger than the CO2 emission that mankind does. So there is a very large carbon cycle on this planet. And we add a very small one that has, however, significantly higher efficiency.
Okay. You can still ask your questions on Slido. But Professor Schlögl, let me turn my last question around. How much of our chemicals can be produced by CCU in the future? I mean, if we want to get independent from fossil carbon sources, will we be able to cover everything by CCU?
Yeah. This is, I think, no fundamental problem. The issue that is forgotten in this discussion is that when we have such a cyclic operation, then we need large amounts of additional energy, because the price that we pay for keeping carbon in the loop is, of course, we always have to add a significant amount of energy. That means the consumption of energy of the chemical industry will be multiplied as compared to what we see today. But then we have no CO2 emission. But there is no fundamental reason why we cannot generate everything that we need in the chemical industry from CO2 and hydrogen. Whether we do this, that's another question, because complicated molecules we might have in a shortcut way from biomass and hydrogen. That is something to be discussed. This is an intensive type of research, but I can assure you we can certainly have a complete chemical industry that lives on CO2 and hydrogen.
And so probably, I guess, from what you told us, we have also to consider the whole system, because we can put the hydrogen into the steel mill or into the chemical process. And you said, well, CO might be the better reagent for the steel. So there have to be systematic approaches. Is that what you're doing, carbon to chem as well?
Yeah, very much so. So I'm very glad that you mentioned this, because the system aspect of the energy transition is in many cases overlooked, because legislation and also politics seems to love to section energy systems into small sectors, as we call them, and try to solve the problem sector by sector. But that is, of course, the wrong approach, because everything is connected with anything. So that means we need an integrated approach, and the integrated approach means we have an energy system that has one foot into free electrons that we generate directly from sun and wind, and another foot that stands into molecules, and these molecules go via hydrogen and then some derivatives like ammonia and methanol and methane maybe. And when we see this, that this is this dual approach, then it is, I think, very clear that we need, of course, a combined and integrated look at the whole thing, and not just this sector consideration as we have it now.
Well, that's really fascinating. I think another thing, we need to network beyond chemistry and plant engineering, and we will be doing so at Achema. So thank you very much, Professor Schlögl, for this insight into the project, and we are looking forward to get much more detail during your talk and the discussion at Achema. So I hope to see you there. Thank you very much for being with us today.
Thank you too. Bye-bye.
And if you want to hear more about the Carbon to Chem project and about all the challenges we are facing and all the opportunities that are arising out of this transformation, be sure to be at Achema on the very first day, on the 22nd of August, because there we will have our theme day on hydrogen. We will have the highlight session with Professor Schlögl and industry representatives focusing on the potential of hydrogen for future chemical production. We will have the opening session of Achema at 5 p.m., focusing on the transformation of the climate-neutral chemical industry by 2050 or 2045. So another big, big challenge we are facing, and you will be surprised how many solutions are already out there. We will have a theme day on fossil-free production, closely related, obviously, on the 23rd of August. And apart from that, of course, everything you expect at Achema, the whole breadth of topics from the lab to the packaging line. So make sure to go to the website, get your schedule, get your ticket, and I'm looking forward to seeing you at Achema 2022.